We're all working together to build quantum computers based on semiconductor chip technology.
How close can we stay to semiconductor technology to really make a scalable, functional quantum computer?
I think we don't yet foresee or oversee what it's going to bring.
We are starting to solve the grand challenges.
We are at the verge of a turning point where also spin qubits will become the leading platform in this race towards building up a quantum computer. That's definitely like the big holy grail of modern physics.
We really want to understand from a fundamental part what's going on. And in order to do that, we need computational power.
There are many problems that are very challenging to solve with classical computer, and the quantum computer is providing a different way of approaching them.
This has implications from cleaner chemical plants to better batteries, also problems in encryption and security. We will need many millions of quantum bits to work together in order to solve relevant problems. I'm an experimentalist researching semiconductor quantum bits. So this is a method to build quantum computers based on semiconductor chip technology.
Semiconductor technology are used, for instance, to make transistors in our computers, phones, laptops, cars, everywhere. And so our hope is now, can we somehow change those transistors such that they can be used to make qubits, such that we can make this quantum computer starting with the quantum processor on a chip.
So you've got a very powerful starting point for scaling up to the millions of quantum bits that eventually will be needed to make this technology useful.
It's still a big open research questions. How do we get to 1 million qubits? And we need to solve really hard engineering challenges on the way. This is a really exciting time.
So there are really many ways of building quantum bits. Take one single electron and isolate it in a specific location in a nanoscale device on a chip, and then use the spin of that electron as a quantum bit. It's very well isolated from the environment, and at the same time we can control it. In the beginning, we had to really develop all of these basic steps. This was the early days to basically lay the groundwork and implement these building blocks for the first time. So at the moment, people are realizing devices with hundreds, sometimes even thousands of quantum dots. At the level of operating the qubits, we're still not there. It's more at the level of a handful or a dozen, maybe a few dozen. Each and every one of them is a little bit different. Qubits have personalities, and I love personalities in people. I love it that we're all different. But for qubits, it means that you need to work to talk to each and every one. And that brings an overhead. You need to deal with it.
If I want to scale up the platform, you need a large number of spin qubits. Most of the qubits have different characters, different personalities. This comes from material disorder and variability. One of the big challenges that we are tackling is kind of get rid of this character and make them very uniform. So when we have an idea, we first try to understand it qualitatively, if it will work, if it will make sense to explore. And then we dive into some proper simulation to see if everything will work as we expect. We try to understand why it works and why it doesn't work. So we try to build an intuition. And then from the model that we made of the material, we then model the actual spin response. And we try to deliver an architecture that would work for billions of qubits. Make it such that other people then can build it.
Once we have a qubit, we also need to manipulate it and control it. So in my group, we focus on actually the manipulation part. what happens if I slice different signals and see how it will change its trajectory. The real world is not perfect. So if I want to do a kind of operation which flips one of these qubits, it might not do a full flip, but maybe only 99% of a flip. And these kind of residual errors, if you leave them uncontrolled, can actually stack up. The smaller the error, the less error correction you need. This means fast operations. However, if your operation is too erroneous, you cannot do that. If we have little errors already from the beginnings, we need less overhead and therefore we have a better scalability in order to build a quantum computer. If you have 1 million qubits, you need 1 million control lines or more than 1 million control lines. This is something which is very complicated. So the idea now is to reduce the amount of signals which we need to control the qubits.
Until now, all experiments in our field are done with electrons in fixed locations. We call them quantum dots. So one direction that we've been very active in at QuTech in the past years is to explore what we can gain by making electrons move on a chip.
So it's doing two things, right? So first, it's creating space between the qubits, which may help to simplify the wiring thereof. Second, it gives a very high connectivity. We suddenly start to be able to interact with qubits that are much more remote.
This is what we call spin shuttling. So you literally take an electron, displace it over the chip in its potential minimum, and you do it preserving the spin state. And we've found that this can be done with high fidelity.
In the shuttling process, we see dynamics, which are already qubit operations. So this is maybe another ingredient that hopefully in future we can really take to our advantage. The promise of this shuttling and this is that the manufacturing becomes easier while the performance of the quantum computer goes up.
Almost every experiment has gone faster than I expected and has worked better than even I had hoped. And it gives me a lot of encouragement to really push this direction further and see where it can bring us.
So I would say we are in a stage that we have a really beautiful milestone. We can preserve the fidelity, we can move the wave functions around, and now we need to think about how to do that in a much, much bigger spin qubit quantum computers.
Okay, yeah.
And as our chips are getting more and more advanced, this is getting less manageable for humans. As a human, I would just look at sometimes a two-dimensional image. But if I have a 16 parameters, looking at 16-dimensional image is very hard for me. For AI algorithms, this is not a problem. Nothing stops me from storing data in 16 or more dimensions and just introducing it to the algorithm like that. So instead of doing it the human way, we just sort of train or use an algorithm that can tell us how to change all of them at the same time. What we strive for is that our model-produced data are so good that the trained researchers cannot tell them apart. That's how we know that we did something useful. So there is this very living connection from theory to code to experiment and all the way back. And combining all these things, that's just like super exciting.
All the ways from the materials development to quantum devices, nanofabrication, all of this comes together in this effort here, and I think that's very special and super powerful.
This is not something that a physicist alone could resolve.
Walk through a corridor and you have engineers, computer scientists, physicists. You have essentially everything.
We go towards a common goal of having this quantum computer. The spirit is very collaborative.
And only if things come together across the full stack will we have a useful technology. And that is really what we're trying to make happen.
If we can get there, it will change quantum industry forever.
We need to believe that it will happen. We do believe that it will happen.
What we would like to have in a future quantum processor is to have millions of qubits. That would really be a breakthrough.
Brainstorming with colleagues, coming up with novel ideas, testing them in the lab. Combine that with the prospect that this can really deliver a technology that's going to impact the world is really what's been motivating me.